fantastic people, and a big thank you to the last group for presenting our intro for us. So we're just going to jump to the fun stuff. This is the problem that as we move into the personalized genomics era, we're relying on next generation sequencing to allow us to target therapies to cancers. The classic way to do things is to use a matched normal sequence to allow us to infer somatic mutations and to infer germline mutations separate to that. And without a matched normal, the accuracy for inference goes way, way down. But the SMUSH color, as we call it, allows us to essentially leverage the link read data from 10x genomics in order to try to call out the germline versus the somatic mutations using only the cancer tissue. And this is really important because oftentimes that matched normal tissue is just not available for various different reasons. Here's a real-world example. It's difficult to decide whether this variant here is somatic, based solely on this classic tumor data. However, with the 10x data, we're able to separate this out into two different haplotypes as well as a group of unphased reads. And from that, we can tell based on the variant allele fraction in this haplotype that this is indeed likely a somatic mutation. So we constructed a model based off of this where we have three key assumptions. First, that the germline variants are going to be most likely pure within a haplotype. The second, that somatic variants will show up with a fraction A based on tumor purity as well as the number of chromosomes on which carry that mutation. And then the third is that there will be an error rate of sequencing, but you can differentiate that from a somatic variant because that's going to be the same error rate in both haplotypes, whereas a somatic mutation will show up in just one of the two. And we built a model off of this using a maximum likelihood model, modeling each of these different assumptions and the process as a whole. We can talk more about that after the presentation if you want to ask in more detail. But essentially, I'll hang up here to talk about some of the outcomes.
Okay, my name is Peng, and in case we are out of time, I just want to thank the organizer for the wonderful opportunity. And also, it's a really good learning experience from all the talented people with team leader Pan. So, in order to evaluate our models, so we use the tumor cell line called HCC 1954, and we have a mixture of the matched normal with pure tumor samples, which sequence the 10x genomics with 200x coverage. So, as Eric mentioned, our goal is to test whether we can detect the somatic mutation without the normal control, but we want to use this as a series of samples to evaluate our methods. So the matched normal with 0% of tumor content served as ground truth. So you will expect with more tumor genomics in the mixture, the somatic mutation, if there is, will be proportionally increased with more tumor genomics. So with that, it translated to, because as we mentioned before, 10x genomics provide information about which chromosome of the mutation occurs. So with more tumor genomics in the mixture, you would expect the differences between the somatic mutation from the germline reference. The difference will increase with more of the tumor genomics. So that's exactly what I did for this is a spaghetti plot showing that the number of mutations, the proportion of the mutations increase with the increase of the tumor fraction here, and each line represents the same position across genomes. So this, without applying our model, this is a big set of the size to evaluate how our model works. So these are like 31 size. We apply the method to see how our model can separate them with germline and somatic. So you can see for the normal samples without 0%, without tumor genomics, only one was misclassified somatic. And with all the rest of the groups, our model correctly identified this highly competent somatic mutation.
So we were very pleased when we got these examples and we sort of had a basic pipeline up and running. But of course, the full complexity of the genome is much more difficult to deal with. So here's the next step where we started looking at our calls against a full set of tumor normal derived calls from another group. And what you're seeing here is the allele fraction of the alternate allele on haplotype 1 versus the allele fraction of the alternate allele on haplotype 2. And so as a somatic variant shows up, what you expect is to show up, for the point to show up along one of the wings of this plot. And so you expect to have one haplotype that's partially covered by the alternate allele, but not completely covered. And so you can see the behavior of our caller, which is the color. Things that are pure alt on one haplotype get classified as heterozygous germline, and things that are in this in-between zone get classified as somatic. We're out of time. Anyway, so bottom line, the actual genome-wide results are very poor, and we started looking into all the reasons why. There's a whole bank of filters that you need to implement to really do a good job of somatic calling, which our method doesn't, but you can use sort of as off-the-shelf plugins. And we found an issue in the phasing algorithm that's specific to the tumor samples that we're going to have to address to get the sensitivity up. So it was a really informative exercise, and thanks to the team.